All right, hello everyone. This is the preview for Physics 231, experiment number 5. In this lab, students will work on building and testing an inverting amplifier made with op amps. So this will be obviously the first time students have worked with op amps or integrated circuits. The op amp that we're going to use is, the LM741. This device is an 8-terminal device, and it looks kind of rectangular. And there's usually an indentation at the top. It'll either be something like this, like a little semicircle indentation at the top, or it might be like a full circle in the top left corner. These indentations are used to specify the orientation of the op amp. It has 8 terminals or pins, and those terminals, there's 4 on each side. The way they count them is the following. The top left terminal is 1, and then you count in a counterclockwise sense around until you've got all 8 of them labeled. Students will want to look at the data sheet for these devices, and so let me just go to what for a second. I'm going to go back for a sec. So here's the course calendar part of the Physics 231 website, and in the top left there in red is a link to a datasheet archive. If you click on that, here's a list of all of the different integrated circuits that we will use during the Phys 231 lab. Most of these will be used during the digital electronics portion of the lab and the final project. But the 741 op amp that we use is the first one here, and if we click on it, the very first thing in this data sheet are the connection diagrams. And the connection diagram that we want to look at is this on the top right here, this rectangular one. So there's 8 pins, and pins 1 and 5, it says offset null. We're not going to use those. They're used for if you want to zero out a small offset voltage at the output, you can use these offset nulls. But that's not a detail that we need to worry about. Pin 8, it says NC. That just means it's not connected. So that pin's not used for anything. The pins we're going to use are 2, 3, 4, 6, and 7. 2 and 3 are inputs. 4 and 7 are power terminals to power the device. And our output is at terminal 6. So if I go back to my drawing here, what we're going to do is we're going to label pin 2 as V minus. This is called the inverting input. Pin 3 is V plus. This is the non-inverting input. Pin 4 is minus VCC, and so this is the negative power. Pin 7 is plus VCC, and that's the positive power terminal, and 6 is the output. So if I was to draw my op amp inside this integrated circuit, it would look something like this, where we're going to have our inverting input connected to 2, our non-inverting input connected to 3, our output connected to 6, and then power terminals are 7 and 4. So one thing to watch out for is we need to distinguish between inputs and power terminals. Right, so there's 2 inputs, they're labeled with a minus and a plus. There's 2 power terminals, they're labeled with a minus and a plus, so it can be confusing. And so the V minus and V plus are pins 2 and 3, and these are the inputs. And the minus VCC and the plus VCC are pins 4 and 7, and these are to power the device. And so typically VCC plus minus is equal to plus minus 15 volts. So also new in this lab is a triple output power supply, and we're going to use these power supplies to power our op amps. It's called a triple output power supply because it has 3 outputs. One of the outputs is 0 to 6 volts. We're not going to use that for this lab. But the 2 other outputs are, one of them is 0 to 20 volts and the other is 0 to minus 20 volts. There's also, on the far right of the triple output power supply, there's a knob that's called something like tracking. And if you rotate this knob all the way clockwise, it will eventually click. And when you feel that click, what it means is that the plus 20 and minus 20 outputs are synchronized, or they're tracking each other. So that means if we set the output to be 8 volts, then we'll get plus 8 volts from the positive output and we'll get minus 8 volts from the negative output. So what we want to do is we want to rotate that tracking in all the way clockwise until it clicks, and then set the output to be 15. And then we'll have plus 15 volts and minus 15 volts that we can use to power our op amps. The other thing I would strongly encourage students to do is to use the screw terminals at the top of the breadboard. And that just avoids having to use a lot of alligator clips connected to wires. The reason we want to avoid that is because if you have a bunch of alligator clips, they can often touch each other. It makes things cluttered, and if they touch, there'll be like a short circuit, which can be bad, potentially could damage the op amps and so on. So I really encourage students to use these screw terminals to keep their circuits nice and tidy. The other thing we have to think about with the breadboards is that, remember, what we have are these like rows of terminals that are connected together. So there's a row, I think it's A to E, right? There should be 5 in a row, A, B, C, D, E. And then there's a bit of a gap, and then there's 5 more terminals, and I guess this is F, G, H, I to J. And then, of course, this pattern repeats when you go down to the next row, and so on. And then there's a bit of a gap between the 2 sets from A to E and F to J. Now, as you know, all of the terminals in a row from A to E are connected together, and all the terminals from F to J in a single row are connected together, but the A to E terminals are isolated from the F to J terminals, so there's this bit of a gap between them. When you're using the op amp, you can't just arbitrarily put it in any spot on the breadboard. So for example, if I plugged my op amp so that terminals 1, 2, 3, and 4 were in like the A column, then that would put the terminals 5, 6, 7, 8 in something like the D column. And that can't work because terminals A and D are connected together, so we would effectively short circuit pin 1 of the op amp to pin 8, 2 to 7, 3 to 6, and 4 to 5. So what we have to do is we have to plug in our op amp so that pins 1, 2, 3, 4 are in an E column, and then pins 5, 6, 7, 8 end up in an F column. And in this way, we won't have any of our op amp terminals short-circuited together. And so our op amp would be sitting in here, something like that. And maybe the mark to mark the top is sitting here. Okay, so just advise the students the difference between the inputs of the op amp and the power terminals, and on how they have to be inserted into the breadboard. So in part 1 of the lab, they'll look at some limitations of the op amp. And one of those limitations is that the absolute value of the output can never exceed a saturation voltage. And the saturation voltage is approximately whatever you power the device with minus about a volt. And if we power our device with 15 volts, then this saturation voltage is something like 14 volts. All right. Actually, I got ahead of myself here. So this is a limitation. There is a second limitation in that at high frequency, we can get distortions and some non-linear behaviors. So what we'll do is, those are the two limitations we're going to look for. Let me draw the actual circuit they're going to build, and then we'll show what those limitations will look like, for example, on an oscilloscope when they're trying to measure this thing. So this is the inverting amplifier. So here we go. Here's our op amp. Here's the inverting input. It's going to be connected to a Vin, which is a sine wave. So this will be equal to some amplitude sine omega t. And so they can set the amplitude and the frequency using their function generator. We'll call this resistor R1. Then the non-inverting input is just going to be connected to ground. So that's nice and simple. And then what we need to do for our op amp is to have a feedback connection from the inverting input back to the output. And I'm going to call this resistor in the feedback loop RF, F for feedback. We analyzed this in class using the op amp golden rules, and so the students already have seen that for this inverting amplifier, the output is equal to minus RF over R1 divided by, times Vin. Another way to express this, that we could take the ratio of the output to the input, and that defines the gain of the amplifier, and so that's equal to minus RF over R1. Okay, in the lab, they're going to use RF is equal to 100 kilo ohms, and R1 is equal to 1 kilo ohm. And so our gain is going to be minus 100. The minus sign is why this is called an inverting amplifier, so that if your input is a sine wave, when your sine wave is at a positive peak, your output will be at a negative minimum, and vice versa. When the input is at a minimum negative, then the output will be at a maximum and be positive. So this is inverting. Okay, so let's go back to some of these distortions that we were talking about. And let's imagine that I had my input, something like this. Here's time, here's Vn, and let me just draw some kind of sine wave thing here. All right, we know that we have a gain of 100, and let's suppose that we set our sine wave input so that this was going from 0.2 volts down to minus 0.2 volts. If that was the case and we put it through our inverting amplifier, we would expect to see a gain of minus 100. So when we're at 0.2 volts, we'd expect to get minus 20. When we're at minus 0.2 volts, we'd expect to get plus 20. But that can't happen because we said that one of the restrictions is that the output could never be above some saturation voltage, which was about 14 volts for us. So if you actually built this circuit and then looked at the output, let me draw my time axis. I'm just going to drop down some zero crossing lines here, just as a reference for myself, something like that. So now what our output would look like is, first of all, it'll be inverted. So it'll start negative, and it'll go negative a bit, and then it'll saturate, and then go back to 0, and it would cross, and it would go positive, saturate, and this would repeat. And these saturations occur at the saturation voltage of about 14 volts. So that's the first thing they should do, is build their inverting amplifier, put in an input that has an amplitude, that's going to cause the output to saturate, and observe that saturation. The other limitation is at high frequency you can get distortions and nonlinear behaviors. So what the manual says is to build the circuit and then increase the frequency of the function generator until you start to see that the output begins to lose amplitude. And so maybe we go to high frequency and we observe that the output starts to get kind of suppressed, like it's smaller in amplitude than we expect it to be. At this point, the manual says go ahead and increase the amplitude of the input and see what happens. And what happens is you get this kind of distortion where the output begins to look triangular. And so they should observe this kind of behavior, something like this. And then it also makes reference to some kind of like nonlinear features. And so what that means is that the output is no longer proportional to the input. So we get nonlinear relationship between Vn and Vout at high frequency. What that means is that Vout is no longer proportional to Vn. Right, and so our calculation for the gain said that Vout was proportional to Vn, and the proportionality factor was minus Rf over R1. If they're no longer proportional, what that means is if we double Vn, Vout does not double. It might increase its amplitude, but not by a factor of 2. So once they've observed these kinds of high frequency distortions and nonlinear behavior, it just goes on to make the point that you should avoid these for the rest of the lab. So if you start to see these triangular distortions, then that's not what you want to see. Your amplitude's too high, and you should decrease your amplitude. Okay, so that's part 1 of the lab. What did I label that as? Part 1, yeah, okay. So part 2 is going to be to measure the absolute value of the gain as a function of frequency. And so not only that, then they're going to plot the log of the gain versus the log of f. And so I'm going to try to sketch here what they're going to see. So this is log frequency, and this is the log of the absolute value of the gain. We expect the gain is just minus RF over R1. If we're looking at the absolute value, it should just be RF over R1. That's just a constant. It's 100. And so we expect to see basically just a constant value here at 100. And that is what you'll see initially at low frequencies. So this would be the log of 100 right here. Log of 100 is 2. But if you keep going higher and higher and higher in frequency, eventually you reach this point where the gain starts to drop. And we can use this to define something called the bandwidth of the amplifier. And the way it's defined is if we were to look at where the gain drops to 1 over root 2 of its low frequency value. So 100 divided by root 2 is something like 71. So we're looking for like the log of 71 here. And if we go across and find the frequency where the gain has this value, I can call this like F star here, then that defines the bandwidth of our amplifier. So the bandwidth is from, say, 0 frequency up to F star, or in other words, the bandwidth is just equal to F star. Okay, so that's part 2. And so what they should do is they should, they should make a bunch of measurements of the gain at low frequency, and these measurements can be spaced out pretty far. There's no point in getting a bunch of finely spaced data where nothing's really happening. And then they should try to quickly find where do they start to see the gain fall off, and then they can take some data along that slope. What they're going to do is they're going to use a Jupyter notebook to take their gain versus frequency data. They'll first plot that on a linear scale. Then they will take the log of the gain and the log of the frequency and make this log-log plot that I've drawn. And then the next thing they'll do is they will isolate this part that is decreasing linearly on the log-log scale and find the slope. And what they're supposed to find is that this slope should be close to -1. Okay, then they're going to do part 3. And part 3 is to change the gain by changing the ratio of the resistors. So maybe they pull out the feedback resistor and get rid of the 100K resistor and replace it with like 50K or something like that. And so then the gain becomes 50 instead of 100. And then what they have to do is to find the new bandwidth. And to do that, they don't have to repeat all the same measurements they did in part 2. All they have to do is make one measurement at a low frequency. Maybe it's at 100 hertz or something that might be low enough. Figure out what the gain is at low frequency, and then increase the frequency of their function generator until they get a new point where the gain is 1 over root 2, and then they just figure out like what is that frequency F star that I'm at, and that is the bandwidth. So for this find the new bandwidth, what they should really do is measure the gain at one low frequency value. Then they're going to increase F until the low frequency gain drops to 1 over root 2 of its value. This new frequency is equal to the bandwidth. Okay, so what I want them to do is they've already measured the bandwidth at a gain of 100, so they have that one already. What I want them to do is get 3 new bandwidths. So get 3 new bandwidths for gains different than 100. Now there's some restrictions, so you want to avoid very low gains. And the reason you want to avoid low gains is because the inverting amplifier has a gain bandwidth product that is constant. In other words, the absolute value of G times the bandwidth is equal to a constant. That means the bandwidth could be expressed as some constant divided by G. And if we make G really, really small, then the bandwidth gets really large. And it could be so large that it ends up being higher than the maximum frequency of our function generator, which is 100 kilohertz. So low gains can have bandwidths larger than the max frequency of the function generator. The other thing you should do is you should avoid very high gains. And the reason for this is that if you have a very high gain, then even very small input voltages will cause the output to saturate. This causes the output to saturate rapidly. So my recommendation is to use gains that are, let's say, between, I don't know, something like 50 and 200. So they already have 100, so maybe they could do 50 and 200, and then they have to get one more, like a 75 or something like that. Okay, good. What the lab manual encourages them to do is to try to find a relationship between the gain and the bandwidth. Now, I happen to have already written it down here, but the students won't know this. What most students will say is that the bandwidth decreases as the gain increases, and that's absolutely true. But a better thing to do is to say that the gain, or let's say the bandwidth, is proportional to 1 over the absolute value of the gain. So if you were to plot the bandwidth as a function of the absolute value of the gain, it would look something like this. This kind of reciprocal nature. Okay, and it may not be easy to identify with just the 4 measurements they're going to do, but if they do them carefully, they can get kind of that curvature working out nicely. Okay, students won't do this, but let me just show you what the gain bandwidth product actually looks like on kind of a plot here. So this is going to be the log frequency plot, and this is our axis, and this is the log of the absolute value of the gain. And we already saw that for the gain of 100, it looks something like this, let's say. So if you go to a higher gain, the bandwidth shrinks. And so if we go to a higher gain, the bandwidth shrinks. So that means this starts dropping off earlier, and actually they'll start to overlap like something like this. And if you go to a lower gain, then the bandwidth gets larger. So this stays flat to higher frequencies and then starts to fall off. And so you can kind of continue this kind of trend. And so the gain bandwidth plot for different gains and different bandwidths looks something like this. Okay, but students won't get that, and they're not expected to get that. They're just going to try to find this relationship between the bandwidth and the gain. So I think saying that the gain, increasing the gain reduces the bandwidth is right. If they can do a bit better than that by showing this inverse relationship, then that's all the better. All right, so that's everything I wanted to say, I think. I will be there on Thursday, so I can help assist in the labs if it's needed. Maybe the last thing I'll say is that this lab, sometimes the time pressure can kind of build up. And I think the reason is because students are unfamiliar with working with these integrated circuits, and so they take some time to get comfortable with them. So if you encourage your students to try to get through this first part where they build the amplifier and look at some of these limitations, if that first part, you can get it done in, say, 45 minutes or something like that. And then when you take these measurements for part 2, let's suppose that takes, 75 minutes. What's 45 plus 75? 80, 120. So that's 2 hours in. And so that leaves them, maybe about 45 to 50 minutes to do part 3, where they have to change the gain and find the new bandwidths. Okay, perfect. So thank you very much, and I will see you on Thursday. If you have any questions, you feel free, of course, just to send me an email or come find me on Thursday. Okay, thank you. Bye.